Thank you. Thank you, David, and hello to everyone out there. I'm John Armstrong. I run product marketing at Tigera, and I'm going to talk about Calico networking with eBPF today. The Calico team has added a new Dataplane to Calico that uses eBPF extended Berkeley Packet Filter. And I'm going to explore that and explain why we did it and what it's all about. Calico, of course, is a leading CNI networking plugin and provides network policy engines for Kubernetes. And we designed Calico from the ground up with a pluggable Dataplane architecture. And we have a general philosophy of trying to use the best tool for the job in each environment. So on Linux, we started with our standard Linux Dataplane that uses IP tables and IP routing. We started there because it's tried and trusted and compatible with a wide range of distros and kernels, and it's also scalable. The routing architecture on the nodes is very scalable, and we were able to scale IP tables to implement our rich policy, and that's where we started. Eventually, we added Windows support to that, and that's part of our commercial offering. And obviously, the salient point there is it supports Windows, but it has a very different underlying architecture. And the policy framework on Windows is very different, but we took the same data model and we rendered it into the Windows data plane instead. And what I'm going to talk about today is a new data plane that goes beyond the existing Linux one and the existing Windows data plane. As I said, we want to use the best tool for the job. The technologies in the kernel are evolving over time, and we want to keep up with that. eBPF is starting to mature, and a big selling point of eBPF is it lets us put fast paths into the kernel. So we can say if the packet looks just like this, then fast path it. Don't send it through all the normal processing, and just do exactly what we want you to do. In one sense, this is about future-proofing Calico. We're keeping the standard Linux data plane, and that's going to be the right one for anyone who's using older Linux kernels and doesn't need or want to go through an uprev process. But when you're ready to adopt the latest Linux kernels, Calico's eBPF data plane will be ready for you. So what is eBPF? Well, it's the extended Berkeley Packet Filter, which may not mean anything to you. It's an in-kernel virtual machine that allows you to load small programs into the kernel to do specific things. And we say this gives superpowers to Linux because they can be really special things, unusual things that a particular area of Linux wouldn't naturally do. So where does the name come from? It was originally a way of defining filters for what packets you wanted to export to user space when you're using a tool like TCP dump. So if you use TCP dump, you type TCP dump, and then it displays all the packets that are flowing through your system one by one as they arrive on a particular interface. And then sometimes that can be a lot of packets. And if you only want to look at some of them, then you can write a filter that says, only show me IP packets, or only show me packets to this IP address. And under the covers, TCP dump uses a Berkeley Packet Filter to make that happen. And that's where the name comes from. But it's been extended inside the kernel. So the name really doesn't fit now, but that's where it comes from. It's become a generic mechanism for attaching programs to particular hooks in the kernel. And these hooks are always event-driven. Something inside the kernel happens, and then it runs your eBPF program. The programs are verified to make sure that they're safe, and they're not allowed to do things like crash, which is great. And they're not allowed to access public tree memory. They're only allowed to interact with the wider kernel through helper functions. And helper functions let you do some interesting things, but they're limited. Each hook only has a specific set of helper functions that it's allowed to use. So maybe a networking hook would be allowed to redirect the packet. But if you didn't have that hook, and if you didn't have that helper function to redirect the packet, then you wouldn't be able to implement packet redirection as a function because you'd be limited using eBPF by itself. So there's a limit to the superpowers, but that's being expanded all the time as the kernel community adds more hooks and more helpers. And just FYI, the easiest way to write one of these is to write a C code in a limited dialect, and then you can use a compiler called Clang to compile that to an eBPF code. So let's talk a little bit about what you can do with eBPF. Because there are a lot of hooks, it has very broad applicability. And one important thing you can do is security. There's a hook called seccomp where you can attach an eBPF program, and seccomp allows you to police the system calls that particular user space programs are making. You could use that to lock down a particular program and say, you're not allowed to access this file because I've checked the name of the file when you make the open system call, or something like you're not allowed to access this file. So there are lots of different options there. Logging and tracing is a big use case. You can hook almost any function in the kernel for logging and tracing, but the helpers that you have there are very limited. You can record a statistic and add to a counter, or you can write a log to a pipe that you can read from, but you can't interfere with the data that a particular function in the kernel is processing. So the upshot is you could have a very broad suite of hooks, but very narrow set of helper functions. And then there's network routing and packet filtering, which are really the capabilities that Calico is using this for. And there's a wide range of hooks that have different capabilities. And what helps us is that they have a range of places where they interact with the networking stack. So for example, there are the traffic control hooks, there are hooks in the routing table, and there are hooks around the kernel. And each of them has different capabilities for what it can do with the packets or the sockets or whatever its native context is. And those are the ones that we've explored for Calico. So before we could add a new data plane, we had to figure out exactly what our data plane would be. You know, what do we want to do? So we did a lot of investigation and prototyping. First of all, we wanted the new data plane to be generally better than the old, and we wanted it to deliver higher performance, higher scale, for example. And we investigated and evaluated various technology combinations beyond eBPF, but eBPF was on our list from the start. We looked at NF tables, which is touted as the next generation of IP tables in the standard Linux way to perform packet filtering and policy. Unfortunately, we found that NF tables was generally slower than IP tables. Although NF tables does have a cleaner API, it has worse performance, at least for our users. We looked at various, also looked at various socket-based approaches. We looked at XDP. It's very fast, but it has a limited set of helper functions that you can use, and it only supports ingress traffic. And for Calico, which supports ingress and egress policy, there are a lot of challenges to using XDP. So we've ended up with eBPF being the best balance. It has a very rich set of helper functions, and with the hooks, we can implement most of what we need to do. So how is this different in terms of user experience? And how does it compare to the standard Linux data plane that's already in Calico? And I've got some graphs to show in a few minutes. So the big question people have is, are you going to get the same user experience? Well, once you turn it on, you should still have the same rich policy language. Calico supports the Kubernetes network policy, and resources also has our additional Calico network policy type, which is richer than the Kubernetes one. We use the same routed approach for packets. We use layer 3 routing because that scales very well, and it's what the internet is based on. And in general, we try to keep everything we can the same as the standard Linux data plane, except where we've identified a fast path. We'll route the packet unless the eBPF program decides it has a faster way of getting a packet through, and then it will send it on the fast path. Otherwise, we'll fall back to the normal kernel processing, and the kernel will route the packet. So that was the recommendation of the Linux kernel developers who worked on eBPF, that you try to think of eBPF as a way to implement fast paths rather than a way to totally replace everything. So it's an incremental set of changes, but very that have a very big impact on the data plane. So we get the same great scalability, for example, like high numbers of nodes, loads of pods, support for workload policy, things like that. And we wanted to design the data plane, the new data plane, with that in mind. And that pushed us in particular directions. But with eBPF, again, the main benefit is to have those fast paths. So one consequence of implementing eBPF is that if a particular packet takes the fast path, then we bypass some of the Linux networking stack. And that means if you have your own IP tables rules that you're relying on, then a packet that takes the fast path may bypass those rules. So that's something to be aware of if you want the most compatible data plane that works with your own rules. Then the standard Linux data plane will be the best for you. If you want to try out eBPF and you're willing to accept that you can't use IP tables for packets that we're handling, then the eBPF data plane is right for you. Now, one big change is we're handling Kubernetes services natively. So there's no kube proxy when you're using the Calico eBPF data plane. The reason for that is once we factored in all the features that Calico needs to support, like microsegmentation, for example, we found that we couldn't really get it to work with the IP tables kube proxy without jumping through a lot of hoops. So we took the difficult decision to import the business logic from kube proxy, and we're trying to use as much as we can of that as we can to implement the actual NAT behavior and load balancing that kube proxy does. So I got some, I'd like to share some graphs with you, and I think this will hopefully provide some further expand on the illumination here. So this graph shows what happens if you put the new data plane on a pair of servers with back-to-back 40 gig links, common high capacity link. And we created a Kubernetes setup with pods, and we ran kubeperf between the two servers. So this is a very simple TCP throughput benchmark that's single threaded. It doesn't use everything that could to the max because it's just set up as a basic benchmark. You can see that the throughput on the new data plane represented by the red bars is a significant change. It's quite a bit higher, especially with smaller packet sizes. And that's because we've reduced the CPU usage per packet when we're using the eBPF data plane quite substantially. You see a significant difference when you're using small packets. And you really need to be up at tens of gigabits to really feel it, to notice the difference. But even at the lower end, we're still using less CPU. So you'll definitely save some CPU in your networking stack with this new data plane. Native handling of services, the first packet latency, the IP tables that keep proxy use a very long list of rules, and IP tables to implement services. So the more services you have, the more rules it has, and that means that the first packet or the TCP handshake for a new connection pays a bigger price. So more services you have, the bigger price you're going to pay in terms of impact. So this graph shows as you scale up the number of services from 0 to 10,000 IP tables mode, kube proxy adds about a millisecond of latency for 10,000 services. So if you have 20,000 services, for example, that would be 2 milliseconds of delay. The eBPF data plane, because it uses a very efficient map lookup in the same way as IPVS, we're able to remove a lot of the latency and keep it flat all the way out to 10,000 and beyond. So you'll see lower latency, but it is only for that first packet. Subsequent packets are all connection tracked on all the different data planes, so they have an efficient path. And in this graph, we perform slightly better than IPVS kube proxy by fractions of a second. Now, native handling of services is going to provide more efficient updates. And we found that our data plane uses a lot less CPU when we're doing updates. This has been a real pain point with kube proxy. And when you're churning, services, kube proxy in IP tables mode has to load the whole IP table up, modify it, and send it back down again. So there's an impact on CPU when that happens. IPVS mode seems to do something similar to that as well. In this graph with the CPU in the middle of the chart, we churned this service over and over for a few minutes. And that generated a lot of load in kubeproxy. But in our eBPF data plane, there's a very modest increase in the amount of CPU used on the system. We measured the total CPU across the whole system with kubeproxy running in the kubeproxy tests, and then with Calico running in the other ones. Now, another thing that we've been able to do, and this is particularly important for those of you who want to combine Kubernetes services and policy. And that's, of course, what Calico is about. One frequently encountered friction point with Kubernetes networking is the application of network address translation, NAT, by kubeproxy to incoming network connections to Kubernetes services, like through a service node port, for example. In most cases, this has the side effect of removing the original client source IP address from incoming traffic. And this means that Kubernetes network policies can't restrict incoming traffic from specific external clients, because by the time the traffic reaches the pod, it no longer has the original client IP address. In addition, for some applications, knowing the source IP address is desirable or required. For example, an application may need to perform geolocation based on source address. So to understand this this limitation further, let's start by taking a detailed look at kubeproxy's default NAT behavior. And that's what's displayed in this slide here. So you can see a request is sent from an external client to an endpoint for a service within a Kubernetes cluster. And this inbound traffic to the service will reach kubeproxy, where two kinds of NAT will be applied. Destination network address translation is used to map the destination from the service or node port to whichever specific pod kubeproxy has chosen to load balance the connection to. And in addition, application of source networking address translation, or SNAT, replaces the client source IP address with a local node IP address. And the SNAT is done so that the service pod will send its response back to the original node, where the DNAT and SNAT can be reversed before the response is then forwarded back to the client. But if the DNAT hasn't reversed, if it wasn't reversed, the client would not recognize the response traffic because it would have a different IP address than the client thought it was connecting to. So you can see that the kubeproxy packet path is fairly complex. And there are actually 1, 2, 3 hops on the way there. So it's somewhat complex. What we've done is we've streamlined this model and applied something called direct server return. So with our eBPF deployment in our Calico eBPF data plane, this model changes. And one of the most significant differences is in swapping out the Kubernetes kubeproxy with native service handling. So in that case, when an incoming connection is received for a service, Calico's eBPF data plane makes its load balancing decision, then forwards the packet to the node hosting the chosen service pod. And you can see it looks like a tunnel. So the forwarded packets are received by the Calico eBPF data plane on the node that hosts the service pod, which applies the DNAT before forwarding to the service pod. So when it applies the DNAT, it changes the destination IP from the service to the pod's IP. So that's the critical part. Because only DNAT is applied, the source IP address is preserved on the request, and the response from the pod has a reverse DNAT applied by the eBPF program. And then once we've done that, using the superpowers of eBPF, we're able to do direct server return, where we skip the hop back to the original host and reroute the response directly back to the client. And that takes out another network hop. So that's a good thing. Just in terms of performance around DSR, this graph shows the improvement in connect time latency and single request response latency by removing that extra hop. And that was this was calculated on our 40 gig test bed that we showed earlier. So direct server return shaves off about a half a millisecond from the round trip time versus using kubeproxy with SNAT and taking your return path through the original host. And again, I'll just go back to this particular illustration to show again how that hop has been removed. So that's an eBPF overview, extended Berkeley Packet Filter for Calico. And if you want to try this out, it's in tech preview, not quite ready for GA, but you can check it out as a tech preview. And this link on the screen will help you to find it. We'll also be sharing these slides if you're participating in today's event, Camp Cloud Native. And I think I've reached the end of my presentation, so I'd like to thank you.